Hello, my name is Jerry Ratka, and I'm a course developer in Juniper Network's Educational Services Department. In this presentation, we'll take a look at the basics of IPv6 addressing. But before we dive into the basics of IPv6 addressing, we first need to explain why we need another addressing scheme. So let's begin with a little history regarding the currently used IPv4 addressing. IPv4 was created in the 1970s and uses a 32-bit address. This amounts to just over 4 billion addresses. At the time, this number of addresses was thought to be more than enough. The depletion of IPv4 addresses was not anticipated back then. But now that IPv4 address depletion has become a reality, depletion must be dealt with and a larger address pool will be needed. Several proposals were reviewed, and IPv6 was eventually adopted as the next addressing option. IPv6 uses a 128-bit address space, which gives us a much larger pool of addresses. There's no easy way to say the full number, so it's best to illustrate the size of the IPv6 address space by showing you the actual number of addresses. As you can see, it is quite a large number of addresses. IPv6 also provides some enhancements, especially in the areas of improved mobility, multicast, and integrated security. Although IPv4 address depletion might sound ominous, the first thing to keep in mind is that there are ways to bridge between the current IPv4-based devices and IPv6-based devices. So IPv4 address depletion is not an insurmountable obstacle. Existing IPv4 addresses will continue to work, current networks will still operate, and there are ways to deal with the depletion of IPv4 addresses. The Internet Assigned Numbers Authority, the IANA, manages the IP address space globally. Users are assigned IP addresses by Internet service providers, which obtain allocations of addresses from a local Internet registry or a national Internet registry or from their appropriate regional Internet registry. In January of 2011, the allocation of 2 IPv4 address blocks by the IANA triggered a policy to allocate the remaining IPv4 addresses between the 5 regional Internet registries. Subsequently, in February of 2011, it was announced that the pool of available IPv4 addresses was fully depleted. At that point in time, only the regional Internet registries had IPv4 addresses to allocate. It was expected that before 2011 was over, each regional Internet registry would allocate all the IPv4 addresses available to them. So it was obviously time to confront IPv4 address depletion and the eventual implementation of IPv6 addressing. Now, if you're unfamiliar with IPv6, one of the first questions you probably have is whether it is compatible with IPv4. Although IPv4 and IPv6 can exist on the same wire, they are not natively interoperable. In other words, IPv4 content is not accessible using an IPv6 client, and likewise, IPv6 content is not accessible from an IPv4 client. So when you run out of IPv4 addresses, you cannot merely start assigning IPv6 addresses. If you want IPv4 and IPv6 devices to communicate, you will need some sort of transition mechanism. Various options and techniques are available, but for now, let's learn more about the IPv6 address format. As I stated earlier, a major difference between IPv4 and IPv6 addressing is the length. IPv4 addresses are 32 bits in length and IPv6 addresses are 128 bits in length. The massive length of IPv6 addresses forces them to be written using a different notation than IPv4 addresses, and also makes an IPv6 address very easy to distinguish from an IPv4 address. If we were to use 128-bit binary notation as the address would appear inside an IPv6 packet, it would be a string of 128 zeros and ones. No problem for a computer or a router to understand, but unruly for humans to read. So first, the address is broken up into 8 16-bit binary sections, as shown in the second address on the slide. But this notation is still difficult for humans to read, so hexadecimal notation, or hex for short, is used to display the addresses in a more readable format. Hex symbolizes 4 bits in each character, and each segment is separated by a colon. Some quick math will show you that only 32 digits, or less as you will see shortly, are needed to represent a 128-bit address in hex. Our IPv6 address example is shown in hex notation in the third example on the slide. Although this notation is much more readable, we can still take it a step further by eliminating the leading zeros. We know that all 8 sections consist of 16 bits each, so the leading zeros can be suppressed. In other words, you and your router will know that db8 is actually 0 db8. This technique is called zero suppression. Zero compression is another technique that we can use. Because it is known that each address has 8 segments, we can compress multiple contiguous zeros as long as we do so within a single 16-bit address segment. When compressing segments, a double colon is used. Our fourth example shows the same hex address with all zeros suppressed or compressed. It is important to note that zero compression can be used only once in an IPv6 address. Similar to the way IPv4 uses CIDR notation, that's classless interdomain routing, IPv6 addresses can be broken into prefixes of varying length, and these subnet prefixes are represented with a similar style of notation used for IPv4 CIDR prefixes, where the IP address and prefix length are separated by a /. The IP address is an IPv6 address in hex notation, and the prefix length is a decimal value specifying the number of the leftmost bits in the address that make up the prefix. Continuing with our IPv6 address example from the previous slide, we show the address as an example with a 64-bit prefix. The prefix itself will be represented as 2001 : db8 : /64. Note that the double colon is required to represent all the contiguous zeros in 16-bit segments. Looking at the headers for IPv4 and IPv6, you can see they are quite different. This is why IPv4 and IPv6 are not natively interoperable. In other words, a device that speaks IPv4 cannot speak directly with a device that only speaks IPv6. But there are some common fields in the headers. The version field appears in both headers. The TTL field shows up in IPv6 header as a field labeled hop limit. The hop limit field is decremented by 1 by each node that forwards the packet. The packet is discarded if the hop limit is decremented to 0. The protocol field is called the next header field in IPv6 and identifies the type of header immediately following the IPv6 header. Next header uses the same values as the IPv4 protocol field. Of course, the source address and destination address fields are used in both header types. As you can see, the IPv6 source addresses and destination addresses are much larger than an IPv4. Now, by design, only a very small fraction of the total number of IPv6 addresses will actually be used. Such a large address space will ensure that addresses are almost always available. Like IPv4, management of the IPv6 address space is delegated to the IANA. As with IPv4, the IANA allocates large address blocks to the regional registries, who then allocate addresses to network service providers and other local registries. Only 1/8 of the total IPv6 address space is currently scheduled for use on the Internet. That's how large this address space is. The rest of the IPv6 address space is reserved for future use or special purposes. The available address space is assigned to the regional registries in large blocks of /23 up to /12 unicast address assignments. The regional registries then assign smaller blocks to network service providers and other local registries, who then distribute the addresses to users. A small fraction of the addresses made available are going to be used for miscellaneous purposes such as reserved addresses. There are 3 types of IPv6 addresses. Unicast addressing identifies a single interface. IPv6 packets sent to a unicast address are delivered only to the interface identified by that address. Multicast addressing identifies a set of multiple interfaces that might belong to different nodes. IPv6 packets sent to a multicast address are delivered to all interfaces identified by the multicast address. Anycast, similar to multicast addressing, identifies a set of interfaces that might belong to different nodes, but Anycast packets are delivered only to the nearest interface identified by the Anycast address as defined by the routing protocol. Note that IPv6 does not implement traditional broadcast addresses. Instead, IPv6 uses the link local all nodes multicast group at address FF02:1. Every IPv6 address has a reachability scope which specifies in which part of the network it is valid. The link local address scope has a reachability scope of only the local link. This means that link local addresses are to be used to communicate between hosts in the directly attached network. The node local address scope has a reachability scope of the same node. This means that node local addresses are used to send packets only to the same node. The global address scope has a reachability scope of the IPv6 Internet. Therefore, global addresses are globally routable and reachable on the IPv6 portion of the Internet. Think of IPv6 global addresses as the IPv6 equivalent to public IPv4 addresses. IPv6 interfaces can have multiple addresses that have different reachability scopes. For example, it might have a link local address and a global address. So in conclusion, IPv6 implementation is inevitable. With the exhaustion of IPv4 addresses, the transition to IPv6 is definitely underway. IPv6 gives us a lot more addresses to work with, and a growing number of IPv6 devices will need to be accommodated. Newer industries might run only IPv6 right from the start. There are simply no more IPv4 addresses left. Yet the current IPv4 addresses and devices are not going anywhere for quite some time. So understanding IPv6 addressing and preparing for its use is essential. When deploying IPv6, you can gain a great advantage by using Juniper Network's high-end routers because IPv6 has been implemented directly into the ASICs. Having IPv4 compatibility in the hardware means that IPv6 packets can be forwarded at line rate, unlike many competing routers. Additionally, the Junos operating system makes configuring and troubleshooting an IPv6 network straightforward. Thank you for viewing this presentation. There is much more to explore regarding IPv6, and Juniper Networks offers a variety of training resources to assist you. You might want to start with the Day 1 booklets. There are 2 available on IPv6, Exploring IPv6 and Advanced IPv6 Configuration. They can be found at www.juniper.net/day1. And there are other resources on the Juniper Networks website, the partner site, and the Learning Academy.
Juniper Learning Bytes. View more at www.juniper.net/learningbytes. They're free, concise lessons on specific subjects, relevant for all skill levels, taught by training experts, and available whenever and wherever you're ready to learn. Juniper Learning Bytes. Expand your knowledge bit by bit.